Before I begin my talk today, I would like to thank the XTUML.org community for organising this series and for providing the opportunity to share with you some of my knowledge of XTUML. If you're unfamiliar with the XTUML organisation, I encourage you to visit www.xtuml.org. Here you will find a community of like-minded members that are actively working with XTUML and are willing to share their experiences with you. As a community member myself, I participate in the ongoing projects to develop tools that support the XTUML approach. There is a growing list of projects we are tackling. I'm sure you will enjoy and benefit from participating. As part of the community's efforts to broaden the shared knowledge of XTUML, a series of seminars called Inside XTUML, a learning series, was started. These seminars are prepared and presented by community members to share their knowledge and experience with others. I want to thank you for joining me, and I encourage you to visit the XTUML channel on YouTube to view recordings of earlier presentations by some of my fellow members. Today, my presentation is on the topic of verification and validation using the XTUML approach. To explore this topic, we will review the principle of model-driven design as it applies to verification and validation. We will then go on to look in depth at the breakpoint features which support these aims. Finally, we will conclude with a case study showing the features in action. In model-driven design, we quite literally regard the model as the golden source of our design. In a conventional development flow, for example, we would use a revision control system to keep track of changes to our textual target language source code. In a model-driven design flow, the source code is not controlled any more than one would control compiled object code in a conventional flow. Instead, we track and control changes to the source models themselves. By making this fundamental change, we eliminate the transcription defects, such as those introduced during the move from informal paper-based UML diagrams to target implementation language. The high precision required of the source model means there is no room for ambiguity. This in turn ensures that design intent is preserved throughout the flow. The golden source models grow as the project progresses, covering more and more of the requirement. The XTUML process is designed specifically to support this growth. We advocate continuous verification and validation so that defects are found and fixed early. This leads to improved progress monitoring because the testing overhead is explicitly included in progress metrics. Because XTUML specifies an automated flow from platform-independent model to platform-specific implementation, the process is more repeatable. By the same token, maintenance is improved because implementation defects fixed in one place lead to an deployment of the fix in many places. In a conventional flow, it would be necessary to go and find the many places in the platform-dependent artifacts where the defect may or may not have been introduced. The uncertainty is due to the lack of repeatability introduced by the manual coding step. Programmers are not robots and often implement things in slightly different ways, making it impossible to assure that a search operation will find every case that needs to be fixed. Because the implementation is derived directly from the model, it is possible to assess the effect of different implementation flows on characteristics such as performance or memory footprint. Just as we might compare the performance of alternative language compilers in a conventional development flow. To meet the goals of model-driven design, the behavioral semantics of symbols used in an MDD design are specified to a high degree of precision. The ability to execute model is quite simply a natural consequence of this precision. A common issue with conventional UML documentation is that there is always a temptation to allow the diagrams to lie fallow while the platform-specific target language is maintained and enhanced. Once the diagrams have diverged from the reality in the target code, the motivation to refer to them drops. The next time a maintenance job is undertaken, the upkeep of the documentation is therefore even more likely to be neglected. Pretty soon, the diagrams become shelfware. With an MDD approach, this never happens because the models are the source. The precise nature of the XTUML symbols eliminates ambiguity. And because the models are executable, any doubts about what will happen if a requirement is modeled in a certain way can be tested under execution. The executability of XTUML models enables an early test philosophy. Results of testing can be presented to stakeholders from day one of the project, providing excellent, high-fidelity validation of the modelled behaviour. Verification is often characterised by the question, are we building the product right? XTUML encourages a development team to begin test early. By early, we mean adopting a test-first philosophy. Executability allows testing right from the very start of the project. In the early stages, both design and tests are platform independent. This means that we do not have to wait for hardware to become available, nor do we have to depend on limited hardware resources later in the project, since many tests can remain hardware independent. As an added benefit, the design itself is inherently portable, future-proofing the product by allowing portability to new emerging technologies. XTUML advocates a test-often policy. The test collateral is reused repeatedly throughout the life of the project to assure that no functionality suffers regression. The test suites are automated so that they can be run daily and against each individual change set. Test suites are expanded throughout the project as more requirements are covered and as we move closer to platform-dependent target language and target hardware. Validation is characterized by the phrase, are we building the right product? For validating against the requirement, we employ standard requirements tracing tools. These tools operate in a bidirectional sense. We trace backwards to assure that all parts of the model are there for a good reason. And we trace forwards to provide an assurance that no requirement is forgotten. For validating with stakeholders, we need a variety of tools depending on the role of the stakeholder. We can, for example, integrate UI simulations with the running model. Depending on the role a stakeholder has, it may be justifiable to extend such integrations to include a human in the loop. So much for the benefits of model-driven design. What about the practicalities? How does it deliver? What is it like to actually run a model? Before we hit the road with some rubber, let's review the XTUML execution semantics so that we all understand what we're looking at in the simulation tool as it is running. XTUML is based on the concept of an inherently concurrent system. Such a system is made up of populations of class instances, each following the rules defined for it in its optionally associated state models. The benefits of using state machines are well documented. In particular is the observation that the indiscriminate use of flags to capture execution history leads to an explosion of states, many of which do not map onto valid application states, a recipe for bugs. Furthermore, state models are much more readable than are the same rules expressed textually, and readability equates directly to assurability. xtUML specifies precise rules about the passage of time and the exchange of events. Delayed events are delivered after a minimum time. How much after is dependent on the characteristics of the target platform. Event ordering is guaranteed from the same sender, but between different senders, explicit synchronization must be shown, or the receiver must be designed to be robust under all possible incoming event orders. This is addressed in xtUML by specifying explicit event can't happen policies. Breakpoint supports the drawing of most xtUML diagrams and symbols. However, only a subset of symbols are sufficiently formal to support execution. These are the component, the interface and its defined messages, the class with its state models, and finally, the computational details are specified using Object Action Language, or OAL for short. We will briefly look at the role each of these UML symbols plays in an executing system. A component is the fundamental unit of execution. The breakpoint verifier tool cannot launch a smaller amount of functionality, and larger configurations are made up of components wired together into a system. Components are thought of as black boxes. They expose only the interfaces they support. Some components define behavior that is required in the final product. Test components are, by contrast, designed to drive other components or component groupings through all of their behavioral repertoire. As a direct result of their black box nature, components are inherently replaceable. You can freely substitute one component with another. This is an important feature when it comes to verification and validation, because it allows us to isolate individual production components with test components. Both kinds of component are reusable. Production components can be reused in different products or in different contexts within the same product. Similarly, test components can be reused multiple times in many different test configurations. Configurations of components are created by wiring them together. That is, by connecting compatible interfaces together to establish communication between them. Components communicate by sending messages back and forth. Messages carry whatever data is required by the application being built. Individual messages are unidirectional. That is, they flow in only one direction across an interface from one component to another. Messages may be either synchronous or asynchronous. A synchronous call blocks execution in the sending component while the message is processed in the target component. An asynchronous call causes no such blocking, and execution proceeds in parallel in both sending and receiving components. For this reason, asynchronous messages cannot return values to the caller. Asynchronous messages are called signals, while synchronous messages are called interface operations. The large number of different messages in a typical design would be overwhelming, so they are organized into interfaces. The grouping is arranged so that the contained messages are coherent. That is, they all contribute to the achievement of some well-designed, high-level goal, reflected in the name of the interface. The interface formalizes and bounds the possible messages a component may send and receive. An interface may be exposed by a component in one of two complementary ways, as a requirement or as a provision. It is this complementary nature that allows components to be wired together. The provision and requirement are analogues of a plug and socket. Interfaces are bidirectional. That is, the individual contained messages need not all flow in the same direction. This enables request-response protocols to be established within an interface. There is one port for each interface a component chooses to expose. The port provides a home for object action language written for each incoming message. This OAL delegates the message to classes and/or instances contained within the component. Alternatively, messages may be directly sent to a target class state model, removing the need to write any OAL at this level. A component forms a black box around a set of class models that define its behavior. Classes and their associations allow the expression of the detailed design of how data will be captured, manipulated, and used by a component. Instances of classes are created at runtime to implement the required data capture. Associations between classes may be established and torn down at runtime. They also may be traversed to gather sets of instances of other classes as required by the application. Individual values are stored in attributes of a class. These values may be manipulated by object action language written in operations assigned to the class. Most behavior is, however, best exposed in the state models. State models capture the dynamics of the application. They are particularly powerful when current behavior depends on past history, and so are a great tool for capturing those application requirements that have anything related to time. State models may be drawn so that each instance has its own history, or they may be drawn so that the whole instance population shares the same history. State models capture, in a very clean way, the responses required to incoming stimuli. The external stimuli are modelled as events which trigger transitions between states. OAL may be written which is run when a transition is triggered and/or as a state is entered. Any data carried by an event is available to the OAL as parameter values. As mentioned earlier, class state models have the ability to receive signals directly from the boundary of the containing component. Object Action Language, or OAL, documents the most detailed manipulation of the values passing through or captured by the running application. OAL may be used to read incoming parameter values and perform computations on them. It may store the results in temporary variables or in attributes of an instance. OAL can select an instance or a set of instances of another class by traversing associations in the class model, or by testing for specific attribute values. OAL has the ability to iterate over instance sets and to make decisions using an if construct. OAL can send events to other instances or messages to other components. Despite its power, OAL is simple to learn, not least because all the declaration of attributes and associations is already done graphically by the class model. In addition, the syntax is focused at the model level. There are no confusing combinations of symbols to learn. Arithmetic operators are all standard. This helps concentrate the model's mind on the application, not on the implementation. However, the most unique feature of OAL is that it is directly executable. Finally, a word or two about time. An important feature of any real-time system is its behavior with respect to the passage of time. In XTUML, platform independence is achieved by thinking of the passage of time in terms of events arriving at some point in the future. The passage of time can either be simulated or progress against a real-world clock. When simulated time is used, all outstanding execution of OAL and processing of pending events, which themselves can cause more OAL execution, all of that is performed until no more activities are pending. Time is then instantly moved on to the point when the next delayed event is due. The event is accepted and fully processed, and then time is again advanced until the next delayed event, until the entire scenario is played out. When wall clock time is in use, execution proceeds as before, but delayed events are not delivered until the delay has passed against a real-world clock. This obviously results in slower execution by design, but it's useful for humans-in-the-loop type of simulations. Because xtUML emphasizes the benefits of platform independence, model simulation can be used to verify behaviors, validate assumptions, and create test collateral from the very first day of a development project. We can create a traditional Hello World type of model quite easily, but an Arduino style Hello World model can show a state model alternating between states, reminiscent of the flashing LED on the hobbyist development board. Computational completeness is just a fancy way of saying that the model has to have a complete specification for the behavior of interest. The only other prerequisite for execution is that any OAL in the model parses without error. Bridgepoint has a problems view that provides a useful summary of all outstanding parse errors. If this is empty, you're good to begin simulation. There are three ways to launch a verification session. You can right-click on your model and choose Launch Verifier in the menu which pops up. This is useful the first time you run a model. You will notice that once you launch, the Bridgepoint environment reconfigures itself with an arrangement of windows suitable for debugging, which you can customize to your own preferences as you gain experience with the interface. Secondly, if you have previously launched and terminated a simulation, Bridgepoint remembers this and provides a shortcut to it under the debug button in the toolbar. To repeat the last launch, it's even easier. Just click on the debug button to relaunch the last session. Finally, you can open the debug configuration editor by going near the bottom of the debug menu. This allows you to specify in detail which component configurations you wish a particular launch specifications to start. By default, after launching, the simulation is waiting for a stimulus to start its activity. There's two ways to provide a stimulus: manual and automatic. The manual way, we use the Session Explorer. The Session Explorer is one of the windows that is opened when the session is launched. By default, it is on the lower left-hand side of the environment. For starting the execution manually, you open the tree in this window and find the activity that starts your design running. Right-click on this and choose Execute. The OAL written in this activity will be executed and the model will become active. To specify automatic execution, we use the Debug Configuration Editor. In the editor, select the launch that you want to start automatically and open the tree to show the components that will be launched. In the initializer column, you will see the word None. Click on the ellipsis button next to this and it opens a small editor with a tree showing the list of messages the component can accept, organized by interface. Choose the required initializer message and click OK. Now when you start this launch, this message will be automatically sent to the specified component. When testing, launching a simulation is all that is required. The simulation output is all that's needed to determine if we got the expected behavior. If the behavior is not as expected, however, we need to stop the simulation and examine its state to find out why. There are several ways of doing this, manually and by setting breakpoints. To manually suspend execution, push the yellow pause button in the debug view. Execution will stop, showing what was going on in each component at the moment you pushed the button. To resume execution, we push the green Go button. Execution will continue from where it left off. Setting breakpoints is a more useful way of stopping execution because you can determine the exact moment at which it is to stop. There are many different forms of breakpoint. OAL breakpoints may be placed at any line of executable OAL, in any activity. Execution will automatically stop at the beginning of the specified line. To set an OAL breakpoint, we simply double-click in the left margin of the editor. You may do this before you launch or during execution, and the session will stop the next time the line of OAL is reached. Additionally, you may set a breakpoint on an event. By default, execution halts when the event is dequeued, but you can change the breakpoint to halt execution at the point the event was sent, if it was ever ignored, or if it ever causes a can't happen error. To set an event breakpoint, switch to the Model Explorer view, right-click on the event that you want to set the breakpoint on, and choose Set Breakpoint. To change the behavior of the breakpoint, go to the Breakpoints view, select the event, and choose Breakpoint Properties. The resulting editor wizard has options for queued, dequeued, event ignored, and can't happen. Finally, you may set a breakpoint on a state. The options here are Stop on State Entry and Stop on State Exit. To set a breakpoint on a state, switch to the Explorer view, right-click on the state and choose Set Breakpoint as before. The default breakpoint is Stop on Entry. This can be changed in the Breakpoint view in the same way as for event breakpoints. However you stopped, once execution is suspended, there is a great deal you can find out about the state of the executing model. You can inspect the values of all variables in the executing model. In addition, you can see all the instances in existence and see the values of their attributes. You can see the current state of any state machine and any events pending for it. As well as being able to view all this information, you can choose to resume execution or to step through the simulation line by line. Each time execution stops, the new values in the system are updated and available for inspection as required. Finally, we can set up elements of particular interest in the simulation spotlight view for easier access and more immediate visual feedback as to what is happening while the simulation is in progress. While execution is suspended, we can view the current value of any variable being manipulated in the current activity. Different values will be present in different contexts in the running model, and we don't want to see them all at once. Since any given set of variables are visible only in a given activity, the variables view shows only those visible variable values. We select between the subsets of variables by selecting different contexts in the debug view. The debug view is arranged as a tree of stack frame-like contexts, so you can click deeper into the stack to see various values from earlier call contexts. The variables view shows all the values visible in a given context. In the view, you will see local variables, selected instances and instance sets, and the value of any parameters visible during execution of the selected activity. If any values are arrays or have internal structure, you can open the tree in the variables view to see the contained values. As well as execution contexts, the debug view shows pending events waiting to be handled. Selecting these allows the variables view to show the values of any parameter data the events may carry. If the variables view shows a set of values filtered according to visibility in a given context, the Session Explorer shows the big picture. It doesn't filter values, but instead organizes them into a tree that you can explore as required. The tree is organized by, from top to bottom, component, class, instance population, attribute and association value, and finally current state and pending events. The tree also shows executable elements so that you can right-click and execute them as required to stimulate the design for testing and development purposes. Like the variables view, the Session Explorer contents are kept up to date as the simulation proceeds, so you can always see what effect execution is having on the big picture. As mentioned earlier, once execution is stopped, you can allow it to progress one OAL statement at a time. There are two flavors of stepping: step over and step into. When you step over an OAL statement, Verifier runs it to completion and stops at the next statement. Events can also be stepped, in which case the event is dequeued and the resulting transition and/or state actions are executed to completion. For many statements, step into behaves the same as step over, but for statements which invoke another activity, step into follows execution into the called activity and allows stepping to proceed from there. Events may also be stepped into, in which case the appropriate transition or state action is entered. The stepping scope is controlled in the same way as the variables view, so you can step at different levels in the debug view. The Spotlight view filters the big picture by allowing instances and classes of interest to be gathered together into one place for concurrent inspection. The current state of instances and classes in the Spotlight are shown highlighted in the state model diagrams if they're showing. To add a class or instance to the Spotlight view, locate it in the Session Explorer and choose Put in Spotlight. This concludes my presentation on verification and validation today. I hope you found it useful and informative. Please check back often for news of more upcoming episodes in this series.